Dear student, in this lecture we will study the effect of chemical environment on the type of electronic transitions. In the previous lecture we have studied there are four types of electronic transitions: sigma to sigma star, n to sigma star, pi to pi star, and n to pi star transitions. As we know that sigma to sigma star and n to sigma star transition are of higher energy transitions because sigma bond is a strong bond. So these transition can only be studied in evacuated region. So we will mainly consider pi to pi star and n to pi star transition in UV spectra. Now, which transition can take place or not on the basis of the extent of transition? We have divided the transition into two broad categories: allowed transition and forbidden transition. Allowed transition means the transition which occur with higher probability, means which can be observed with high intensity. Those transitions are called allowed transition, for which our molar absorptivity constant comes in the range of 10 to the power 4 to 10 to the power 6. In this category falls pi to pi star transition. Now, why pi to pi transition is a allowed transition? Because the bonding orbital pi and anti-bonding orbital pi our orientation is parallel to each other. So, electronic transition is easy. Now, forbidden transition. Forbidden transition does not mean that transition can never take place. Transition can take place, but it will be of low intensity. In this category we have n to pi star transition. It is observed with low intensity. The reason behind the low intensity of n to pi star transition is that non-bonding and pi anti-bonding orbital lie anti to each other, means they are at 90 degree to each other. Now we will study the effect of solvent on the electronic transitions. Uh, Solvent is very important to study the UV sample. Solvent polarity affects the extent of electronic transition depending upon which transition is taking place. For example, first category, effect of solvent on N2 pi star and N2 sigma star transition. Now, if a group attached to the compound under investigation is more polar in the ground state than excited state, that causes shift in the lambda to shorter wavelength. How it shifts the lambda to shorter wavelength, we can observe in this diagram. If a molecule is more polar in the ground state, means our ground state is more polar, then if it interacts with the polar solvent molecule, then ground state gets lower in energy. If it gets lower energy, then energy difference between the ground state and excited state gets increases. Means now energy difference has increased. If energy difference between the ground state and excited state increases, then lambda shifts to shorter wavelength. Initially, we have taken non-polar solvent. In non-polar solvent, there is no interaction between the molecule and solvent molecule. But if we employ polar solvent and our molecule in the ground state is more polar, it will definitely interact with the solvent molecule. That lower the energy of the ground state and increases the energy difference between the ground state and excited states, and our lambda shifts to shorter wavelength. Second category is the in the second section, for example, effect of solvent on pi to pi star transition. If a particular group attached in our chemical compound under investigation is more polar in the excited state than in the ground state, then what happens to the energy level? It means now in the presence of polar solvent, the excited state energy gets lower, but ground state energy remains the same. So energy difference now has decreased in the presence of polar solvent. So lambda will shifts to longer wavelength. For example, acetone molecule absorb at 279 millimicron in hexane solvent. Hexane is a solvent in which we have studied the acetone molecule. Now if we change the solvent, as we know the hexane is non-polar solvent, if we change the solvent hexane to water, now lambda max comes at 264 millimicron. This is the first case, means we are studying the N2 sigma star. It means now wavelength has decreased. Wavelength decreased, it means delta E has increased. Energy difference is increased and lambda is decreasing. So we should select solvent very carefully. So for choice of solvent, there are certain conditions. For example, first condition, it should not absorb radiation in the UV region selected for the study. And second condition is it should be less polar. It should be less polar and it should not absorb radiation under the region selected for investigation. For example, the most commonly employed solvent is 95% ethanol. It does not absorb radiation above 210 nanometer. Above 200 nanometer does not absorb radiations. Other solvents which can be employed are hexane, cyclohexane. The solvent which should not be used for UV spectroscopy are benzene, CCl4, carbon tetrachloride and chloroform. It should not be used. These solvents can be used for UV spectroscopy.